When I was getting crazy, reckless and wild, acting like my mama's little devilish child. It took a heart like yours to find its place. I've been at the wrong place at the wrong time, chasing all the wrong things most of my life. Been every kind of loss that you can't find, but I got one thing right. Been the kind of guy girls' mamas don't like, running with the wrong crowd on the wrong nights. I've been wrong about 1,000,000 times, but I got one thing right. You, baby, I got one thing right. Baby, I got one thing. Yeah, I got you. Baby, I got one thing. I got one thing right. I've been wrong about 1,000,000 times, but I got one thing right. I got one thing right. I've been at the wrong place at the wrong time, chasing all the wrong things most of my life. And every kind of loss that you can't find, but I got one thing right. Been the kind of guy girls' mamas don't like, running with the wrong crowd on the wrong night. I've been wrong about 1,000,000 times, but I got one thing right. You, baby, I got one thing right. Baby, I got one thing. Yeah, I got you. Baby, I got one thing. I got one thing right. I've been at the wrong place at the wrong time.
So I took this doubling every year and extrapolated it 10 years from 1965 to 1975, from 60 components to 60,000 components on a chip.
First thing you have to tell him is, guys, we've been giving you a free ride for 30 years while you write your crummy software and we made it faster, right? That's over.
The future is parallel. Single cores are not getting any faster.
All right, good afternoon. So today we are going to continue our series on memory hierarchy. And today we are going to talk about the roots and the remedies of cache methods. But before we start, it's always a good idea to put all ourselves back to the root cause, why we have to investigate the idea of memory hierarchy, because there is a huge performance difference since 1980s, which is probably the time none of us were on Earth yet, right? And then the gap started to grow in, and turns out that it's so significant that it's at least like 100 times slower between the processor and memory nowadays. So that's why we built memory hierarchy. And originally, it's just a small piece of SRAM, but then we learned that the more levels of SRAMs we have, even though the L3 and L2, they are a lot slower than the L1, but it's better than going to DRAM anyway. So that's why we embrace the idea of multi-level memory hierarchy, and within each different parts, we also make it multi-level as well. So the whole memory system is indeed hierarchical, and there are hierarchy within hierarchy. So and you might think, well, it's just put a piece of SRAM cache in there. Is it hard? And the answer is yes, and it's more complicated than you can ever imagine. So for example, nowadays we have made our cache way associative in a way that the cache is organized as the following components. First, you have blocks, and each blocks use something called tag to identify the current content of the block. And for each block, there is a valid bit, there's a dirty bit. The valid bit means that the data within the block is trustworthy, is ready for you to use. And the dirty bit means the data has been modified. And also to avoid the chance of conflict, we also make the chance set associative. So that's why it's called weight associativity cache. Because with that concept, we organize cache blocks into set, and each set of the cache block would contain multiple, each set would contain multiple cache blocks. So for this slide in particular, each set will contain 2 different blocks. So this is a two-way set associativity cache. And for this particular cache that I demonstrate in this slide, you can see we have 8 different sets. Assume each horizontal line represent a set. So, and each of the block can store 16 bytes of data. So as you can see, assuming that each character is a byte, we can store 16 bytes of data. So, you know, my slide is not making, is not chaotically made. It has a meaning of that, right? So for this particular cache, each block has 16 bytes of data. So you need 4 bits to address any byte within a block. And because we have a total of 8 sets here, so you need 3 bits to identify a set within your cache. And the rest of the bits will be used as the tag. So it will be used for us to see if that's the block that we are looking for in a cache. So whenever you receive an address, we will partition the address into block offset, set index, and a tag. And we use the set index to identify which set we want to access. We use the block offset to point out where the word we want to access. So it turns out for this particular cache, we go to the set that the set index indicates. We use the selector to select the block offset that we want to output. So the conjunction of this would be the word that we are outputting or not. And to decide if we are selecting any output from here, we have to judge if the tag stored here matches the data that we are accessing. So we use the tag field that we identify here. We find out that this part is what we want. So then it turns out that we could have the left-hand side output as our cache search result. So that's the idea of weight associativity cache. And you might feel like, oh, how do I know how many bits I need in a cache, need to partition the cache, the address for the cache? Then I give you a very simple formula, C equal to ABS. Not sure how many of you ever see this sign on your car, but ABS is a system every car should have. So if you really cannot remember that, you can say, well, every car should have an ABS system, right? And for the ABS, the C is the capacity of your cache data array. And the A is the weight associativity we have in your cache. So like the previous example, we have a set containing 2 blocks. So we have a set containing 2 blocks. So it's a two-way associativity cache. And for direct map cache, because each set contains exactly 1 block, so it's using 1 for direct map cache. And the block size means how many bytes can you store within a block, or how many bytes can you store within a cache line. And S means the number of sets. And there is a special type of cache called fully associativity cache, which means that your cache block can go anywhere within a cache. So in this case, you should consider the whole cache as one big giant set. So you can use 1 for fully associated cache. Otherwise, most of the time, S is probably an unknown that you have to derive from C equal to ABS. So in particular, for so use C equal to ABS, you would be able to you would be able to partition the memory address. And after you are able to partition the memory address, you will be able to see, well, if it's a hit or a miss in L1 cache or not. And once you figure that out, depending on it's a hit or a miss, your system is going, your memory hierarchy is going to deal with them differently. So if it's a hit in the label that you are searching for the data, you can just return the data to the requester. However, if it's a miss, you have to go down a label to find for your data. However, most of the time, you are not that lucky that your cache is not completely empty. So you have to find a victim block to accommodate the incoming block. And sometimes the victim block that you selected from policies like LRU would be dirty, meaning that if I kick out the data directly, then the data will be missing. So you have to write back it to the next level of memory hierarchy. And during the write back process, there is a potential that you also need to trigger other cache misses as well. And after that, you will fetch the block that you want. However, it's also possible that the block that you are fetching is also a miss. Then the same process repeats. That's how that works. And the process of writing data is pretty similar to the process of reading data, except that the only difference is that you always perform writes on the first level cache and set 30-bit whenever the data is written. So that's a difference. And the last lecture, we finished at this shocking fact that NVIDIA Tegra X1, this is a processor used by Nintendo Switch. This is a processor used by Jetson Nano. The cache hit rate, or say the cache miss rate of this particular pieces of code, which I'm trying to do some calculation on 4 different arrays, and using the C equal to ABS, I partition every address that I want to access into tech index and offset. And turns out that if you try to iterate on this address sequences generated by this code, this particular pieces of code, everyone is a mess. So for this particular pieces of code, which you probably would write most of the time, the processor doesn't perform them very well. So isn't that surprising to you, right? So now today we are going to continue our series and see if we are going to know why we have such a misses. And with that root cause, we are able to improve cache performance. But before we talk into the root cause, maybe we can have some hints here to guide you why the code would have such bad performance on the previous cache configuration. So let's look at another processor that we have. This is Intel Core i7. And I encourage you to go through the same process we have in the previous question to answer this particular question. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so for this question, I definitely see a demand of discussion among groups. So I have sent the question through the chat. So now let's go ahead and start discussion. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so now let's see what you guys have. Well, I think you guys are divided into two. So some of you were unmuted. Are you trying to say something? Guanji, are you trying to say something? Okay, if you don't mind, I will mute you. All right. Which team would like to share your thoughts with us? Okay, so I have Hayat from Team Blue. I remember you. Now, can you share your thoughts with us?
Yeah, so we started with, we didn't get enough time, our group didn't get enough time to solve the whole thing, but we started with C is equal to ABS. And so the cache size is 32 kilobytes again, so 2 raised to 15, and it's 8-way set associativity, so that would be 2 raised to 3. And the block size is 64 bytes, so that's 2 raised to 6. and that would mean S would be 2 raised to 6 as well. So we have 6 bits offset, 6 bits set index, and the rest of the bits would be the rest of the bits would be the in the
Tag.
address. Yeah, tag.
Okay.
Yeah, and after that is the point where we got lost.
Okay. So anyone would like to continue? So Team Blue, give us this part. So then what's the next to do? Kevin?
Yeah, so once you set all of that up, you can, set out your memory layout if you want to visually, right? Where it's going to be now your set size is 8, right? So you're not going to have impacted, you're not going to be reading all of these. So the difference from the last problem is you're not going to be overriding, like when you start to load E, you're not going to be overriding A, because even though it's going to have the same same index.
Yeah. So slow it down, right?
Okay.
So if you don't have the information regarding the previous question,
Sure. Okay.
what's the next to do after this?
Let's just split it up then, and then do one instruction where we load everything in, I guess, so we can see it all right.
So we have to create the address sequence that we are going to access.
Yeah.
Right. So that's the reasonable next step, right? So for this type of question, the first thing to do is figuring out how many bits are there in each field of an address, and then produce the address sequence, right? So the first address to load is.
So let's load the first 5, I guess. So the first is going to be A sub 0, which is going to be 10000. And it's going to have the tag 0, right? Or sorry, it's going to have the tag 10, and the index is going to be 0, and it's going to be a miss. So we have to load it in. And then we're going to load B.
Okay, that's fast forward. I believe up to here is pretty similar to the previous one, right?
Now we're going to load E sub 0.
It's probably here.
Yeah, so once we load E sub 0, it's going to have the same index 0x0, but with the tag 0x50. And it's going to be a miss, but it's not going to be replacing your last recently used, which is A, because you have, it's 8-way set associative instead of 4-way. So you have 8 different memory or 8 different blocks you can cache blocks that you can use to index 0 for the index 0. So you're going to load it in, and it's going to be a miss, but it's not going to rewrite, or it's not going to override A. So then when we load A sub 1, it's going to be 008, and now it's going to be a hit instead of a miss because A wasn't unloaded, right? So it's going to be a hit, and every, the first or the second element, right? The, at index 1 of every single array location is going to be a hit now because you're not overriding it. So
are we going to hit forever?
We're not going to hit forever. So these blocks, like the array for like the A array right here, the array is much bigger than the actual block size, right? So a block is 64 bytes.
We are still, if we are at 7, we are still good, right? But if you keep going on, we reach 8 sub 8.
Yeah,
right?
So now
here's the address.
Yeah, so A sub 8, the block size can only hold 8 doubles because it doubles 8 bytes, and the block is 64 bytes, so it can only hold 8. So when you load the 8, it's going to roll over. The address is going to roll over from the offset, from the incrementation being from the offset in the green here to the blue. And this rollover is going to change the index. So now that we're changing the index, it's going to be a miss, and we have to load in an entire another block.
Right. So it turns out that for this pieces of code, if you have the Intel processor, right, you are going to see a miss for each array, each 8 array element, right?
So yeah, it's just gonna be
So
1/8.
if you know this, then you can calculate the miss rate in a way that is now 1/8, right? And that's actually giving you the number of 12.5% in our code, right? So we only have miss when the rate index is the multiply of 8. So that's why we got 12.5% as the answer. So Hayat, do you have other questions? Don't you
Yeah, I
agree
had a
with the
question.
okay?
From the point we start from a sub 8, then do we
Mm-hmm.
not replace anything since the block is all 8 blocks are also full?
Well, but it's a different index.
Yeah, it is a different. Okay, yeah, fair enough.
Yeah, it's a different set, right?
Yeah.
So we have to replace a block within a set if the set doesn't have more blocks to accommodate this one, right?
So
So you can
we're just
consider
moving
a
to the
set
next.
as an apartment, right? Now, if you want to have a new roommate, you definitely don't want your roommate to sleep at the same bedroom with you. So you definitely have to kick out a roommate, right? So the index is the apartment number. Make sense?
Yes, thank you.
All right. So now with this question, the answer would be 12.5, right? So you see the power of different processor design way that, well, increasing the weight associativity from 4 to 8 actually make the performance a lot better. So your cache miss rate reduced from 100 to 12.5. And now I'm going to show you a real demo on the machine. So this is a Jetson Nano machine that I have. So if you get the CPU info, you will see that it's RVA processor. And now I'm running the code that so let me make clean. Well, actually, I can make dash f make file .tegra. So in this way, I would have the Tegra version of the code, and which is compiled on the machine. And to save our time, let's run the optimized version of the code. And for these pieces of code, if I define A, which is the which if I run version B, which is well, so I did some operation change here is because, well, and actually I don't think it matters. Okay, so let me change the operation that I have here to be consistent with the code that we see. And the iteration I have here is a variable, but we can definitely ignore it for now. So to make it consistent with the code that we are having. So and the reason why I have to do this is because I want to show you that. Let me do one more thing. Tegra. Okay. So one thing that I want to do here is because I want to demonstrate that what's the original number of oops. What's the original number of cache misses we have? So let me run this version of the matrix opcode, which doesn't contain. So for this matrix opcode, I don't run this loop. And the reason why I have to specifically create a version is because in the very beginning, we have a lot of initialization code that already put the value of A, B, C, D in. So I want to let you know what's the baseline cache memory accesses without without that loop. And the tool that we are going to use here today is something called Valgrind. So is it? Let me do it. So really fast. Array size. Okay. If I don't define it. Okay. Oh, okay. So it will work. Okay. So the program Valgrind is a tool that can use to generate those stats. So for this one, the baseline has 21 million data references, and within which we see there are 5 million of them are cache misses. So, and this is the data access we have for initializing those arrays. So now let me run the version of the code that we have for adding a loop. So as you can see, right, we add a lot of memory. So we add about, so this, the original number of DRAM references is 21 million, and now we have 104, well, almost 105 million. So subtract that, we got about 104, 1 minus 21, that's about 84, right? And we got 84 million more data memory accesses. And the original number of L1 misses is about 5 million. And now with this new addition of 84 million data memory access, we also get 84 million L1 cache misses, which is a good enough indicator to tell you that every additional memory accesses that we created from the loop that we have in the code is actually a miss. So this would prove that, well, even though we are using this cache simulation mechanism by hand, it reflects that 100% of the misses we have here, the loop will create 100% of cache misses. So hopefully that will give you a good enough idea that, wow, it's indeed that for this pieces of a code that professor is not lying on the real machine. There is a machine that has 100% of misses there. And now I also have an Intel machine that I can show you. So this is an Intel Core i7, Core i5 processor. And if you want to know the configuration of its cache, you can basically do this. And I believe the lab should also give you this kind of practice before. So for this, right, you do see that the cache size is 32 kilobyte, 8-way associativity, 64-byte blocks, right? So exactly the same as what I gave you in a question. So now let me show the same demo again. And for this guy, I also have, so here's the make file I have. And again, let's use Valgrind. And okay, so we can use Valgrind now. And for Valgrind, the same tool. Do I have Valgrind installed here? Okay, it doesn't look like you. Okay, so we can run Valgrind here again, --tool, cache grind, and we can run a program called, again, the baseline program, the baseline matrix op, which, ooh. Okay, the baseline matrix op. Okay, so again, the baseline matrix op has 21 million memory access, 5 million of them. So this part, initialization code, is exactly the same as the JSON Nano. But now let's look at, for this pieces of a code, what does it look like? Why is, oh, Okay, what does it look like on the Intel machine? Okay, see, with the Intel machine, the cache miss, the number of cache misses we have is only 10 million. But remember what we got before on the Jetson Nano is actually, wait, Jetson Nano, we do have a number, right? Yeah, with Jetson Nano, the number of L1 cache misses is actually 89 million, right? So the same code, different processor actually have huge difference in performance. Hopefully this demo will give you a very good insights about, well, even the same code and the same GCC compiler, the same -03 optimization, right? It's optimized, right? I still see 100% of the cache miss rate for this piece of code, right? So it's not something that a compiler can do for you. And if you don't do it by hand, then that's not going to help you, right? So now I'm going to talk about, later on, I will going to talk about how can you improve the performance of this pieces of code. But before we talk about that, before we talk about the remedies of a problem, it's important to know the cause of the problem. So that's why let's look at the cause of cache misses. And in fact, there are 3 different types of cache misses, and we call them 3 C's of misses. So the first C is the compulsory miss. And the compulsory miss means the cold start miss. So thinking about that, right? If someone asks you some name that you have never heard about, then it's definitely something that you would never know, right? Like before taking CSE142, if somebody asks you about, have you ever heard about Professor Usagi, or have you ever heard about Hongwei Zhen, right? You probably know, what is that? What is that thing, right? Then that's definitely something not in your mind. So that's compulsory miss. And so first time access to a block in the very beginning is definitely a miss. So this type of miss is called compulsory miss. And the second type of miss is called conflict miss. So it means that the data that I'm accessing was previously in the cache. However, for some reason, and the reason is typically because your cache block replaced by other blocks within the same set. So the data were previously here. However, because there is a conflict in the set, so the data got kicked out. So right now, when I access the data, it becomes a miss. So this is a conflict miss. So this is pretty much similar to a hash collision problem. And now, the last type of miss is called capacity miss. So the capacity miss, as you can see from its name, it's just because the cache is not big enough. So if today your code just want to visit a lot of data within a very short period of time, in the very professional jargon is that if the working set size is bigger than the cache size, then it's going to be missing anyway. So for example, this is summer session. We only have 2.5 weeks before the midterm. And if I try to teach you the content that even a regular quarter cannot accommodate within 10 weeks, then nobody is going to ace in this class because it's impossible for your brain to remember everything, right? So this kind of stuff is like a capacity miss, but the capacity is depending on the capacity of your brain in the short term, right? So same thing for the cache. If your application have so many stuff, give it up. It's not possible to do it well, right? So how can you tell this is a capacity miss? If you don't increase the cache size, the memory access is still a miss, then this is a capacity miss. Or another thing that you can test is that even if you make the cache fully associativity, means that there's no chances of conflict miss, because conflict miss means that while the cache is replaced, the cache block is replaced by others within the same set. However, for fully associativity cache, there's no such a concept of set. And even with that, it's still a miss. Then it's completely a capacity miss. So there are 3 types of miss: compulsory miss, conflict miss, and capacity miss. So for simulate a direct map, if we go back to the question that the example that we have in the very beginning about simulating a direct map cache, right? Given this is the address sequence, we partition the address into tag, index, and offset, right? The first access is definitely a compulsory miss because the first time we access a block, and then the next one will be a hit, and then when we access the third address, it's a different index. So when we look into that set, there is no such a block there. And this is the first time we meet this block in this pieces of code. So it's definitely a compulsory miss. And for the third miss, again, this is the first time we meet this combination of tag and index. So it's definitely something we meet the first time. So it's still a compulsory miss. And for the second last address, right? We have a miss here, but remember this pair of tag and index were previously visited. So it was in the cache before, right? But for some reason we cannot keep it. So it's a conflict miss. So that's the difference between conflict miss and other misses, in a way that conflict miss must be something that we have seen before. All right. And for two-way set associativity cache, right? If you simulate that, you will figure out that compulsory misses are still there. However, because you have one more block within the same set, so the conflict miss is not there anymore. All right. So now, for this particular question, can you tell me how many cache misses are conflict misses in this question? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so for this question, I do see we probably need some group discussion. So let's go ahead and start the group discussion. All right, let's wrap up in 15 seconds.
Professor, the poll is not up yet.
Oh, shoot. All right, so now wrap up in 15 seconds. Five, four, three, two, one. Time is up. Okay, so now I have Jing Ning Zhang. Would you mind to share your thoughts with us?
So we think it's D.
You think it's D, but how you get the answer of D?
So first, we know that we need to load A0, B0, C0, D0. And since they are always the first time we see, so these four are compulsory miss. And then when we load E0, it will kick out A0. And since it's our first time seeing E0, it will also be a compulsory miss.
Okay.
And then we will start to load A1. When we load A1, we kick out B0, but since A1 was in the was seen before, so it is a conflict miss. And this pattern repeats from A1 to 7, B1 to 7, C1 to 7, D1 to 7. These are all conflict miss. And then when we load A8, B8, C8, and D8, they are all compulsory miss. And this just repeats. So it's like 7 conflict miss in 8 misses.
Right. So every 7 out of 8 will be a
Yeah.
conflict miss, right? So it turns out the cache miss rate, well, the percentage of conflict miss among all the misses will be 87.5%, right?
Yeah.
Okay, awesome. So now, okay, Team Red score 1. So now let's go ahead and look into what about Core i7? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so for this question, I do see a very diverse answer among your group. So go ahead, group discussion. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so I have Hayat. What do you think?
So we discussed in our group and we thought it's E 100%.
Okay, okay.
Because from E, when we load E sub 0, we're not rewriting A sub 0, we're not replacing it, and that's why that would also be a compulsory miss. And after that we would have hit still E sub 7, and after that we changed the set, so we're accessing the new set for the first time, so those would also be a compulsory miss.
Right. So if you write down the address sequence like this, right, you will figure out that, well, the first few access to those block with those addresses with offset zeros, they are all compulsory misses, right? And then even though, and then it's all hit, right? And now it hits until we meet another block, and this other block is something that we have never visited before, so it's still a compulsory miss. So then turns out that every miss in this Core i7 processor is essentially compulsory misses. So for this particular pieces of a code, for this Core i7, 100% of the misses are compulsory misses. So all misses here are compulsory misses. That's the short answer, right? So that's why the answer to this question is 100. All right. So I think through these few questions, we are all good with the definition of methods. We are all good in evaluating the performance of pieces of a code. So now, the most important thing is that being a programmer, how can I write code to improve my memory performance? So the first type of, the first set of optimization that I want to introduce is called loop interchange, fission, and fusion. So we have seen loop interchange before, right? So if you don't remember, right, the left-hand side performs better than the right-hand side, even though they have the same complexity, the same instruction count, and the same processor. And now you know the reason is because for the left-hand side, and according to the cache layout, right, according to the spatial locality, right, the if you are incrementing J here, right, so 0, 1, 2, 3 is within the same row, and if you're in C programming language, it's the row order major indexing method. So then it turns out that if you are trying to change the row in the index, the column index within a row, it's going to make your access sequentially in a row. So the cache block is aligned with the row orientation. So it will give you better spatial locality than the other one, which we try to change your row index frequently, right? So which is very, very inefficient in terms of the cache cache organization, because we cache data within a block, and for this part, it's definitely always a mess. So that's why the right-hand side has worse performance than the left-hand side. And if you don't trust me, right, you can definitely use Valgrind tool again on the code that we have sent before. But to save our time, I would probably leave it for your own practice. And now, let's look at this code, this problematic code, right? You have seen, whoa, cache miss rate 100%. If the only thing that I can use, like I work for Nintendo, I work for NVIDIA, and I work for Tesla, for example, right? And Tesla uses NVIDIA's processor. And then I really want to make my code efficient. Then how can I make this code efficient, right? Then how can I improve the cache miss rate? So let me show you another version of the code. Can you tell me if we change the code like this, what do you think it would change the performance of cache? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so I do see there is a need of discussing this particular question. So why don't you guys go into group and start the group discussion? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so Hayat, do you have an idea about what your group is thinking?
Yeah, we think it's 80% still.
Okay, how did you get that?
So for the like when we iterate through the first loop, we load up A, B, C, and then store to E, right? So those four would be misses, and then after that, as if we access E again, that would be a hit because E is already in the cache, and D would be a miss. So D sub zero would be a miss. So I think it's five out of every six accesses are misses. So that's close to around 83%. That's I'm not sure, but that's what I think. That's what we think. It's around 80%.
Okay, Kevin. Kevin, you raise your hand. Do you have a different
Oh,
thought
sorry,
about
I
them?
forgot to unmute. Sorry. Hello. Yeah,
All
so
right.
you actually don't access D in this first loop at all. So you're
Right.
only accessing A, B, C, and E. So because of that, you eliminate in this first loop all of the conflict misses. Because since it's four-way set associative, you are never loading a fifth tag with the same index there. So you're gonna have
So for this pieces of code, right, we have four-way cache set associativity, but it's good because for this loop, we only try to access 4 elements at a time, right? So for each iteration, and we are going to repeat the whole loop before we go into this one, right? And so for this, we only have compulsory misses, right? Which occurs every 1 out of 8 for each axis, right?
And then we have the second loop. So the second loop here is you're going to be accessing 2 elements. Now, E sub I should be in the cache, every element of E sub sub I for the entire array, because the entire array from 0 to 511 will have been loaded and it was never flushed out or never, made invalid. So it's going to be in memory already for all of these. Then we access D sub I or D sub 0, let's say, and D sub 0 is going to kick out. So now when we access D sub 0, we are going to have, well, it's a compulsory miss because we never loaded D in, but also your set is going to be full. So you still have to kick something out and you're going to kick out the A sub 0, but we're already done using A sub 0. So we're never going to load that in anyways. So we're going to load D, and then because we're just accessing E and D now, they're both in memory for the first 8 loads there for D, and then it's going to be again the 1 out of every 8 miss rate when you're compulsory miss rate when you load D in. But E's already loaded everywhere. So the second for loop has a 1 out of 16 miss rate, I think.
Right. So awesome. Right. So Kevin is team yellow, I believe. Yep. So here's the thing, right? So looking at this, we only access 4 elements within an iteration. And so we have a total of 512 iteration. And here we access 4 array elements. And every 8 out of this 512 times 4 will be a miss, right? So that's this part. And for the second part, right, we create a total of 512 times, actually, I would say 3, right? Accesses because we load E, load D, and then store to E, right? But as Kevin just mentioned, right, if we are lucky enough, and indeed we should be lucky enough, because if you look at the size of E that we traveled, it's 512 elements times 8 bytes, and it's actually 4 kilobytes. And if you pay attention to this configuration, it's a 4-way cache. So on average, for each way, there will be 8 kilobytes. So it's definitely under the threshold that the E will be kicked out. So every E will still be in a cache, and you will kick out other things because the last element that we accessed in this loop is actually also E, right? So it's very unlikely E would be the least recently used in any of the set. So it turns out that E will be there forever. And then whenever you load a new D, it will kick out either A, B, C or something, right? So, but it's still a compulsory miss. And you will have every 1 out of 8 access to the D as the compulsory miss. So it turns out that's your total memory access, and this is your total misses. So for this part, right, it's 512 times 7. And for this part, we can do some cancellation. So it's 2 times 512 plus, well, 1/2 times 512 plus, this is what? This is 1/8 times 12. So it's 512 times 7. And this is 256. And this is 512. This is something like 64, right? And so this would be 64 times 8 times 7, and this would be 4 times 256, well, 64, 5 times 64, right? So cancel that out. So it would be something like 5 over 56, right? So it's pretty close to 10%. So the answer to this question is actually the miss rate is close to 10%, right? After some calculation. So this kind of technique, changing the code, like dividing a loop into 2 to improve cache performance, is a programming technique called loop fission. So we are separating a single loop into 2. And now I'm going to show you the demo of the power of loop fission. So let me SSH to that Jetson Nano machine we have. And again, go into the CSE142 demo memory loop. And now let me make the code consistent, right? So this is the version of the loop fission we have, right? And I don't think I need to explain too much, but you should be convinced that these 2 pieces of code, they will generate the same result, right? Because I'm just separating them in 2 different loops. So again, I'm running this optimized version. So previously, the optimized version is called matrix of B, and you already seen that with the matrix of B, we still have 89 millions of cache misses. And now let's use ball grind to run this optimized version of the loop, or say the loop optimized version of the code with the loop separated, right? See, right? Previously, we have a lot of cache misses, but now it's only 11 millions, right? And now if you try to use matrix of B, which is also a -03 optimized version, you will see it has like 89 millions of cache misses, right? And the other thing is that it's also surprising, it's maybe a little bit surprising to you, is that both of them turn on the -03 optimization, but the compiler cannot change the code from version B to version A, because again, we mentioned, although there are compiler optimizations, but compiler can only optimize your code in a very limited scope. And it's very unlikely the compiler can do this for you. So I would say this is more like a programming technique that the programmer has to take care by themselves. So this is called loop fission. So now I'm asking you, what if we change the processor? So today, if I'm not running on a code on the Jetson Nano, but I run the code, both versions of the code on Intel processor, do you expect this optimization to make any difference or not? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, looking at your answers, I do believe we won group discussion. So go ahead and do it. Let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so Jingming, you have some answers that you want to share, would you mind to unmute yourself?
We kind of feel like it might be D. My reason is that, first of all, A and B has a similar miss rate as we calculated before. B probably have like 12.5% miss rate, and A is like 11%, so it's pretty similar. But for A, you have to access EI twice for each calculation, and for B, you only do it once.
Okay, so I saw some of you also raise your hand. Like Hayat, do you agree with Jing Ming, or you have other thoughts?
So initially I thought it would be E because they have similar miss rates, but then one of the group members, Chris, I think, yeah, Chris said that there's less memory references. We're accessing E less times in B, so B would perform better.
Okay, so let's look at what if we run it on an Intel machine, right? Again, I have this Intel machine set up. So why don't we just, and I already have the code, right? Both versions of the code. Why don't we just run it on the machines? And this time we are asking for overall performance. So it's not just about the cache misses, and let's time it, right? So that's say, well, let's run optimize up 03, and well, because there are some initialization overhead, so I want to run it for maybe 10 times so that we can get better estimation of the time. Wait, am I getting it? Oh, no. Okay, so what was that? Okay, so this is probably, all right, running it for longer, right? So I give it a pretty big array. And for this is the version A, right? We split them into two different loops, right? So it's matches up A, well, matches up C. And if I define A, then it will run the split loop, right? So as you can see, for this pieces of a code, okay, let me give you one more zero, right? It's about 0.5 seconds running that iteration for 10 times. And now, but I do remember that I made some modification to the matches before. Yes. So here, let me run the version B with optimization flex again. And you will see for B, right, it's only 0.4, right? And previously for matches A, for the version A, is statically at 0.5. And both answers will give you the same answers, right? And as many of you discussed, true, right? For this Intel processor, because the cache performance is already good, it can make no only compulsory misses in this code, and there's nothing else you can do better than the cache would do for this side, right? But on the other hand, for this piece, since memory, which is the one that incurs the most of the latency, so the memory is not anymore an impacting factor. However, for version B, because you have one more access here, even though it's a hit, but it's still an instruction. And the for loop itself also have more instructions. So now it falls back to the instruction count, right? You have more instruction count, and if the CPI is about the same, then this version will give you worse performance because it has more instruction count. So that's why for this particular question, the answer would be D. So I'm glad to hear that a lot of you got it. And that's why compiler optimization is so difficult, and because it's very hard for the compiler to guess what's the right thing to do given different architecture, and it's complete depending on the programmer's choice. So before you leave the classroom, there are several things I want to let you know. So again, assignment 2 due upcoming Sunday, and midterm next week on Thursday. And I know a lot of you were complaining about that. Oh, I'm not in the time zone that you are in, so that's why I cannot attend office hours. I cannot attend the lecture. I cannot attend discussion sessions. Okay, I hear you. So here's what we are going to do. The midterm next Thursday was starting from the lecture after Wednesday until 3:20 p.m. on Thursday. So you have about a 24-hour time frame. Within this 24-hour time frame, pick any 80-minute slot. You have only one shot, and you will be online, and it will cover material up to next Tuesday. If you have other questions, feel free to come to my office hours. Other than that, enjoy the rest of the day, or I will see you in our
I've
Professor,
cheated and I've lied. I've broke down and I've cried. I've got
Yes.
nothing to hide
yeah,
no more.
there's sorry, the
I've
music's too loud.
loved and I've hurt.
What?
Yeah,
Hello?
there's 142L lecture in 40 minutes, right?
Yes.
Okay, thank you. And is that uploaded on YouTube as well?
Yes, it's
Okay.
always.
Thank you so much.
I've cheated and I've lied. I've broke down and I've cried. I've got no